Yeah, you I kind of want to really focus on that. On stable with the facts and trying to like needed on their compensation to extend this sorry, yeah. It made me feel like
There's a way to do it,
like
just actions like.
I was thinking all this stuff on playing or phones. Exactly. Or parents are like Vegas.
Well, it'll be like a well picture that then like this thing.
So I'm like, find it, but afraid. Yeah, and also I think like
That's the
like,
way it will be.
Oh, given that in a way like if people are different like
Oh, nice.
you need to know it's just kind of basic. If you get right terminology, but you're gonna be like, so you often put the door with the other on the board, I mean. Rather than like faith. Like, yes, but it'll be like this party. Party. Rather than like, easy. Like there must be some more integrated way of. So like,
Yeah, it's good type things. It's like very effective.
yeah, but you don't have to really interact with it in any like directed way. You know, if you say something in cases rather than like using it like useful. Way. So like maybe feel like I needed to spend less time talking about like physically doing things, or trying to just like talking about that good. So that's what I'm doing. I don't know, like I feel like I always kind of skip that a lot of the, well, I don't spend enough time with it that like what to actually like. I also think there's so little, like when you take, one of the weird things, you take a math class, or when you go like read math online, like the amount that they start so low. And you have to build up like reams of stuff that is just so like it's never gonna be useful. And like what actually is useful is like very circumspect. So to like narrow that down. But I don't know, I tend to be like
I think we.
Dude, every time I forget it's her. I missed it.
But I say that, but and really, but that's actually, yeah, unless you become. Businesses. To get there, so like,
yeah, I feel like that's really interesting thing you said. It's a really experience. Exactly what it's like. You don't need to bring it. Might be exciting for people. Guys. No. Yeah, I mean, I think so, but there's another thing that actually is missing. Which is the, like, like, when you're doing that, like, growing with nobody actually solved it that way. It's in a very different way. And so but the translation of the theory of taxes is also like absent in any, like most things are not solvable analytically. Yeah, but it's this. It's like, you make.
Yeah.
Yeah.
You did try. There you go. The other one. Yeah. I don't know what it. I'm over here. Yeah, I don't. You don't.
Really good brand.
What you get? What are you gonna do?
Big gap. Okay. Hey guys. Oh yeah.
Like it's cold shower.
Yeah.
Right. No, I don't think
I downloaded new versions of uploaded new versions of the same file. So if you have them, please download them. Good thought.
Oh, wow.
Is the shared version.
Yeah.
Every song that I'm gonna say on this real. Those things. She's gonna be worse than Elizabeth.
Yes.
It's.
Advantage.
Thanks.
Getting a lot.
Oh, it's pretty good. Batteries wired.
I think I don't believe that will kind of why, but you might have like there are things that you need to fix angles. There's like wire bending that have like fixed angles. There's like they're like little pegboards that you can bend a wire around it and like fixed angle and make like a little 3D printed thing. And you like always bend it the same thing. Or they sell them, they're like a wire bending gig. So they keep doing like yeah. Yeah. Yeah, even with the fact that you can't control that. Yeah, you can do a precise bend with a jig. You know, make your own jig or you get a vise with an 8-7. Like, it's not that hard to find. They're like a little indenting around. Yeah, that's good. We will schedule like that's why I will tell you. Talk about this. I don't think I can go through everyone's thing and I think that's not useful. So like I think people like as soon as like this evening I will like these pops out when there's a ways. This is exactly what I want. This is totally this is 100%. What's it? And then not that was cool. Yeah. I think you did great. It was exactly like it was totally in the thing. I played on it. His value of your research like that more. That's right. How to apply it. But we'll do that in clips. You drew it with your part. So yes, Yes, you should, yes. If you don't have your laptop, would like to follow along with me, get it.
Cry. Like an article. Take it home.
Okay. It's so nicely brown. That's what they call it. It's full pop. Yeah. Okay. Hey everybody. Okay, so about the assignment, I've got emails from people saying, you know, some people did it, other people tried and it didn't work, other people like, you know, they're like, next please turn it in later. I'm not super stressed about this. This is supposed to be a starting conversation. So what will happen is I would love to go through them all in class together, but I think it's just not viable. Honestly, it just doesn't work in an hour 15. We will do that for the next one, the prototype. I'll have outside people and we'll look at them and talk about them. But for this one, everybody just needs to schedule an office hours in pair. That's what we will do. I will this evening. I will post office hours for the next couple of weeks, and every single person needs to group with another person, and needs to come to office hours, and discuss, with me like your next step, basically. Yes. Material test. That would be amazing. Yeah, that's a great idea. You know, last year, I think I just manually showed some of them in slides. But you know, maybe I should maybe it'd be faster if I made a mirror board and you guys could post it. I think that would be easier than me exporting them all to JPEG. So I think that's what I will do. And then for the next one, that one we will go around the room and talk about them in class. We will not get to everybody, but like we will just go around and discuss. And then we will do another round of office hours between that and the final. Okay, so everybody will have like that's the only way I can think to do it. Okay, but they look exciting. And you know, I will be more I will work with you on it individually, so that we will figure out what to do with them. The goal is how to apply them or merge them or repeat them or something to make shapes. Okay. All right. So what I want to do today is just keep going through what I was doing last class. I wanted to keep going through kind of foundational ideas in parametric modeling. The one other thing I did want to say is this guy, Martin Perrier, he's at the MFA right now. He's really amazing. Like he does things that are very similar to what we're doing. They're like giant, you know, kind of geometric sculptures made of like this is an active bending structure. He's really interesting. Like he does them on these like large formworks and then kind of removes the formwork. They have really interesting joints. This is a very interesting thing because he has a completely idiosyncratic and personal way of interpreting objects, of creating objects and creating a form language. It's very it's strange because he spent time in Sierra Leone and he also spent time in Switzerland. So there's this weird
like hybrid kind of vocabulary that's totally personal. I don't know. If you have 10 minutes or 2 hours, I would recommend going. It's really cool. Okay. They're giant and exciting. All right. So what we talked about last time, just again, a recap, I always do this a little bit, is this idea of like working with objects, object-oriented programming, the idea that there's an input and then there's an object that knows a bunch of data internally, knows it has some functionality, the outputs are passed to another object, which stores the data again, and then passes it to another object. So each thing knows something about itself and it knows how to do something and passes it along. And then also this thing that I forgot to mention, that you can look at Grasshopper in two ways with the names, the full names, or just the icon display, and that I always am showing mine in the full names, but you can change that. So at the top in the display mode. The other thing we talked about, this idea, which I think is the most important idea, that a surface is two-dimensional and that its three-dimensional shape is a map from its two-dimensional self-knowledge to the three-dimensional world. That's what a function is it maps, what a parametric function is it maps something from the UV coordinates, which are essentially planar, to a 3D form. And that the same is true for a line. A curve is a map from a 1D space into a 3D space. And so when a curve has one parameter, one identification number, which is the t. And that, by the way, I didn't say this last time, that is why this command flow along surface does what it does. It just takes things in one UV space and transfers them to the other UV space. So it doesn't, the spaces are completely unrelated to each other. It doesn't matter what shape this is. It just, this has UV coordinates and this has UV coordinates, and it just duplicates the UV coordinates from one to the other, because every NURBS surface is four-sided, and so it always has U from one number to another number and V from one number to another number, and you could translate that into another surface without any with an enormous amount of distortion, but without any difficulty, because there's just a one-to-one translation of the coordinates. We talk about this idea of parametrization, which is that there is the domain of the particular curve from, in this case, 95.6 to 470.4 is the address signature of the t numbers. And if you go to reparametrize, always for both surfaces and curves, that will take that from 0 to 1. And we also talked about that idea of using this evaluate a curve with the parameter to get either the perpendicular plane or the curve or the tangent at the point. And then lastly, we talked about this idea of series and range, which are two different ways to get lists of numbers like that. Okay, so I want to talk a little bit more now, moving on. Please download the new version of the same document in today's date. A little bit about lists and trees. They get very complicated, but essentially Grasshopper stores things in lists. A list is just a long list of either numbers or integers or vectors or surfaces or anything. And when you compare two lists to each other, it just compares the first numbers for a while. And then when you get to the end of one, if it doesn't match up with the other, it just compares the last one to itself. And I'll show this practically in 1 second. And then the other idea that's important is this idea of a tree, which is a list of lists. And what happens with the tree is it will compare every item in a branch of the tree to every item in another list. And this is what causes the crash, is where things get compared hundreds and hundreds and hundreds of times. And so matching up the data structure of one to the data structure of the other is what causes it to work or not work. And this is complicated. It's the hardest part of the whole thing, is trying to get the data structure to match up with each other so you get the right comparisons between one list of things and another list of things. You just have to get the right things to line up with the other things. And this is the only thing I would say that is really tricky. And for the most part, this is why I try to keep things simple. Because if you get, I don't like sitting around, trying to rearrange my data structure and then it if I change one thing, it'll all fall apart. So for the most part, the things that I show you today, I try to work with very simple data structures. If I can't get it to work in a simple way, I'll come up with a different way of doing it. Okay. So just to give an example of that, if I go into, by the way, I didn't used to do this in quite the same way. I used to go through my models first. And then, so it was much more focused on the physical modeling. And then I would just give you a lot of scripts. And then I would also go through the Grasshopper kind of like more quickly. And I've decided to do it a little bit differently, which is I just want to go through what I think are the important concepts and record them and do them in front of you, because I think there are lots of concepts floating around. And some of those concepts really don't matter. And other ones I think kind of do matter. And so I want to go through the ones that are important. And I want to go through the physical models sort of one by one in a way, if there's time. I'm not sure there's time, but one by one through the idea of the parametric modeling so that you can see sort of what narrow part of it I apply to the physical model. That's the idea. That I like when I make some of these physical models, I think it's important to apply a small amount of parametric modeling around a few key concepts. My idea is to show you, if I can, in the time that I have, what is I thought was useful and how those things were created. Okay, so in this is the stuff I went through last class. Some of this is new. It's essentially a different version of the other thing. So in here, if you have a curve like this, let's hide these. If you have a curve, you go set one curve. And then if you do a divide curve, it will make a list, right, of points. And if you look at the parameters, you can see there's a long list in here, okay? And if I wanted to make a sphere at each one of these points, I could do like a sphere, and I could give it a radius, and that will make a sphere at each one of these points, okay? And if I change the number in here, it'll change the number of points in the list. If I wanted to make spheres of different radiuses, I could make a list of radiuses and compare them to the list of points. So I can do that just dumbly with something called merge, where I can just merge. Let's put a 5 in here, and let's put a 12 in here. And then if I look at this, like this, you will see there's a list of 12 and 5 and a list of 8 points. So if I put this list of 12 and 5 in here, it's going to compare them to each other. And the first one, it's going to use the first one first. And then since this list is shorter, it'll just compare to the last one. Okay, so this is kind of like the basic comparison of the lists. You can see how this works. It's just kind of like comparing one list to the other, like that, okay? But then if I were to say, do something else, if I were to convert this list into a tree, which is done with this thing graphed tree, if you look at it now, it will be 4 independent lists, each with one item in it. So before it was a list of 4 items, and now it is 4 lists of 1 item. And you could have, you could have lists of several items and whatnot. Now, if I put this grafted one, you can also graft things by right-clicking and going to this graph. And flatten will smush it all back to a single list. I rarely flatten, but I often graft. So if you put this in here and you zoom in here, you'll see that it's doing one of each radius for every single point. So it's comparing the list to the tree in that way. So essentially, what it's doing is trying to match up the structures effectively. And this is, it does it with some, this default behavior that I'm saying. And this is very useful because let's say I had two curves and I wanted to have a different radius on each one. So if let me just, now instead, let me delete this so it doesn't work. If I were to go here and go set multiple curves, now I have two curves, each with multiple points. And if you look in here, there are now two lists. It by default created a tree. There is now two lists, each with 8 points on it. And so if I were to now make a list of 2 and graph this, if I look at this, you can compare the data structure. So this has 0, 0 signature. This has 0, 0 signature. That one's 0, 1. This one is 0, 1. And if the data structures match up, the behavior is predictable. So if I were to put this in here, it's going to make, do the one radius in is going to the 3 is going to match up with the 3 here, and the 0, 0 is going to match up with the 0, 0 there. Okay, so this is the thing that gets confusing, is that it becomes challenging to get these structures to match up, and that is because as you work on Grasshopper, it keeps adding zeros here. It keeps adding and changing the data structure. And it's not like actually that organized, and that's because when they were developing it, they had to make certain kind of priority decisions about when things wouldn't be added and when they would not. Okay, so but this is the main idea, is that there's lists and trees, and if you look in here at this param viewer, which is right here, this thing that looks like a tree, or you can double click and go param viewer, like there, that thing. And you put this in here, I can see it says it's data with 2 branches, and they each have 9, or I can go to draw a tree, and it will show me like a little graph of a single thing branching into 2. Okay? So when something doesn't work, this is usually why. All right? But I tend to try to keep this as simple as possible. And often when I'm working on things, I'll just do the same setup twice on different surfaces. Okay, so then I wanted to kind of go through a couple of more tools for this. So there's graphed, like I said. There's also flatten. If you right click and you flatten this, it will kind of smush it all down back into a single list. And there's also shift paths, which takes an integer number and will, it will change the, you can see it changes the number of, it shifts the tree by 1 in either positive or negative directions. So many times you'll see things in my scripts like where there's graphs and there's shift paths. This is nothing to do with anything except trying to, get the number signatures of the lists to line up. And you remember this component, because it was acting on 2 things, by default, it created a tree. So you have to kind of compare the data structure and make sure that they line up. And I usually in my scripts try not to do the little arrow graph. I try to put like an actual one in so that you guys can see it when you're following along. Okay, so that is the first thing. And then I wanted to talk just a little bit about selecting things from lists, because that comes up a lot. So if I have like a bunch of items like this, and I kind of make a container for them. Now remember, these are poly surfaces. So a poly surface is now forevermore called a boundary representation. And so like if I do what's called a list item, I think I just have to type item. Yeah, there it is. List item. This takes the index and returns a single one of them. So this selects the fifth item. It's actually the sixth item. 0 is the first one. Selects one in the list. And if I wanted to select two things, I can go in here and add. And then I could do, let's select the next two with a little merge. So that is how you kind of get items out of a list, by doing this list items thing. And then, so I do this a lot. You'll see that in a lot, this list items thing. You can also reverse the list. You can reverse it. And then the first one is now the last one in the list. And then the other thing I do a lot is I will select every other item in the list. So if I take this curve, and I do the same thing I did before, set one curve, and then I go divide curve, and I put in like, I don't know, 25. And then I do this thing called a dispatch. This takes a pattern of true falses. If you kind of mouse over it, you can see it says true false. So you can change that. You can change it by right-clicking and going set multiple Booleans and typing them in here. Or you can do a merge and do these Boolean toggles. It's false, true. And then this one outputs all the falses and all the trues. So this little thing, I usually use it just to split lists. So if I put the points in here, you can see it's getting every other point. Yeah, there is random. Yeah, like you can do like random. It's a little more tricky. You can generate a list of pseudo-random numbers. Like, and then you could use like, so I could do a range from, this would take a range from like 0 to 10. And then this takes like the number of random values that I want. So if I just wanted one, and then I would do a list item. So like I could do a domain from 0 to 10. And then it's going to give me a random number. And I could use that as the selection. But yeah, you can do that. There's other ways too. I think you can do randomly remove n items from a list. But I usually only use this dispatch to make alternate things, and then I'll do, I don't know, like draw a polyline. That's a polyline now from every other point. And if I wanted to flip it, I would often just, I'll often just manually go in and like remember that there's a part of my script that can cause things to flip. And I'll just kind of like group it and say like flip here or something. Something like that. Okay. All right. Is that clear? A little bit. I'm trying to, the pacing is hard for me. I never know whether I'm going too slow or too quickly. So, and some feedback is helpful. Okay. All right. So, all right. So then what I wanted to do now is an application, because I think, by the way, I think I've shown you enough that you can do most things that you need to do in this class already. Okay. So like, since many of your models are poly surfaces, and you can't use the evaluate surface component that we used last time. You have to get points on them in a different way. Like if you have a poly surface like this, you can see I could go brep, load it in. Let me turn these off. Uh, and then I can go brep deconstruct, and that will take the individual surfaces out of it. And then I can do list item to select one or two of the surfaces. So, but that is sort of very manual. It's kind of like going back to, then I would have to if I look in here, I would have, like a list of 3 or 4 surfaces, 5 surfaces, and I could plug that into a script, and I would have to manage the data and make sure that, things work out correctly. But, what I think most of the applications we're going to be using, often just about making holes in things, making bolts. Okay. And so what I will often do is, like I'll just make a bunch of points. Let me turn these off. Okay. So this is kind of an application. Let's hide that. Okay. So if I wanted to make some bolts on this thing, what I would often do is just make some points on it manually. So I might, get some isocurves. I could even manually divide them, get a bunch of points. And then I can use each of those points to make a kind of a normal bolt to the surface using Grasshopper. So here I'm going to do the same thing I would do before. I can do brep, set one brep, and then I can do points, point, set multiple points. Now I have a long list of points, and I have a single brep, and I can do brep closest point. Take these points, drag the brep in, and that gives me some information about the surface. It gives me the closest point, and it gives me the normal to the surface. And then I can do the same thing I was doing in last class. I can just do this SDL from the first point in the direction of the normal times a certain distance. And then I would get these kind of normal things. And then the other thing I will often do, so they go through the surface, is I will scale them from the endpoint. So I do this operation a lot. I'll take the endpoint of this line and just scale it by 2 from the endpoint. So I'll do this other thing, endpoints, take the endpoint, and then the scale is asking for a factor, a center, and a geometry, which you think about it when you type scale, it asks for the same thing. It asks for a base point, a factor, and the geometry. Okay, so it's just kind of like a literal, super literal version of the yes. I mean, so there are zillions of ways of doing everything, but it often depends on what you want. So I was going to do another application, try to build up in kind of complexity. But often, I want to start with basically, if you can't get it to work by arraying the bolts around the surface of some pattern, just do it this way. You don't have to do it manually. You can automate 10% of the process. So I think when you're using these things, I think trying to automate 100% of it is a mistake. I think you automate the most pain in the ass part first, and then you kind of, work up to that. So yeah, I mean, first of all, I could have just divided these points from the curves rather than doing the curves manually in Rhino. Or I could have extracted all these curves from the surface in some way, either by contouring it or by extracting the isocurves. Or I could have just divided the surface down. There's the divide surface component. But in terms of locating them in the right spots, I think that's the question. And so like, if you automated too much, there'll be like 3 of them that aren't where you want them to be. If you automated too little, it's annoying. So I think there's a tension between those two. But yeah, I do want to do that. I will show you like another method for doing it in 1 second. Like, so here, like if you just take the endpoint into the center, the line into the geometry, a factor of 2 into the factor, and then I can pipe this by what would be the radius of whatever the thing is that I'm doing. Whatever my joining material is. Oops, that's pretty skinny. So there you go. Okay. So that is like the very, very simplest way to make bolts onto a poly surface. Then I would just bake them, split them out manually, and unroll the thing. I don't think it would be this. It would be whatever you've panelized. So that, the thing is when you panelize something, it's often not a single surface anymore. It's often got very complex like topology. And so figuring out how to put things on it is sort of complicated. But like this really, what I'm trying to convey is that to do tiny operations requires a very low lift. And if you want to like learn the software and learn the process of designing your algorithms, I think doing little things is the place to start. Okay. So like, and then, also, then you could ask me and we can figure out how to automate more of it. Okay. So yes. So let's say in this example here, let me hide this here. I think what I did is, this is a poly surface, so it has multiple things. So harder to just extract the isocurves from it directly because it's many surfaces, so you can't just extract the isocurves. So here I'm going to do a B rep, set 1 B rep, and I'm going to do a contour. And this takes a B rep, it takes a start point, so I need to, I don't know, give it some points. So I will often do that just manually. Just give it a point. It takes a direction, the direction of the offset. So I'm going to do a unit Z, which is the world Z up. Put that into the direction, and then let's do a distance. So let's do something big so I don't crash. Okay. So now I've got a bunch of curves on a surface. I could have done that manually in Rhino by doing the contour function. And then one thing that I have done, which you all should have, is in the main Coon, there's something called shorten curve. And this is so that you don't get bolts in the little ends of curves. So you can pump the contours into the shortened curve, do like a point. Let's do 0.5. It will shorten all the curves. Maybe need more than that. Let's do 10. It will shorten all the curves by a little bit. One thing that you will notice is that every single component duplicates the data. So the old curves are still in here, and I have to hide them if I don't want to see them. So now I've got a bunch of short curves. And then I could divide all of these down. I could do divide curve. Let's do 15.0. Let's do 8 bolts. Okay, and now if I look in the data structure here, I should have a list for every single curve that has 8 points on it. So very quickly, I'm getting lots of information in here. That's because if I looked in here, there used to be already grafted, there used to be 13 curves. And now when I did the divide curve, it did it on 13 and created 13 lists of points. So usually before I plug things in, I will look at what the structure is. Now, these are just the points. And so these parameters don't relate to the surface at all. They're from the curve. So if I want to get the normal to the surface, I have to do the same thing I did previously. I can do a B-rep closest point, go back, find the original B-rep, plug it in here, take all these points, plug them in there, and then I can just do another line SDL from the start point in the normal along the direction. Okay, so essentially this is the same script I used last time. It's just starting to add functionality. Does that make sense? Anyway, this little thing is for contouring of VREP and adding normals. So there's a slightly more complicated version of this, which is in, by the way, I'm progressively uploading my model file. So like this is the model file for the tower thing. These are what it looks like, the double layered tower. So this has two double layers of surfaces offset. So you can kind of see the modeling process in here. If you are interested in how I made one of them, I'm uploading them kind of progressively as I get to the level of complexity that I think we're dealing with. So in this one, I just had like a long, I have these two kind of back-to-back surfaces, and they're made with all of these grouped strips of things, and they are shifted on each other. So like every other one overlaps every other one by half. And so they need to be bolted here and there through each other. And so the first thing I think I did is I, downloaded a model of the rivet that I was using, checked the diameter, scaled it up so that I thought it would work. And then this is the script that applies the bolts to these. Exactly what I've just been doing, but it's slightly more complicated because in this case there are many surfaces, and I wanted to get this alternating pattern of bolts. Okay, so in this case, I think the original version that I did exactly what I had just done, where I contoured it. But I wanted to make something that was a little more general in functionality. Like, let's say you didn't want to, only have, let's say you have a model that's kind of complicated, and contouring it in one direction doesn't make sense. Like, how would you apply bolts to a complicated surface like this in some kind of alternating pattern? So I think what I did first is I just this is the manual part, just contoured it twice, like using Rhino. But these curves could have been made some other way. So these are the curves that I want to apply bolts to. I want to apply a bolt here, and then another one, a quarter of the surface, another 3/4 of the surface, and skip the half surface, which is where the back of it is hidden there, right? So this is there are two ways to do this. Okay, so let's say I have all these curves. I can either in Grasshopper, since I want to take every other curve and apply an alternating pattern, I can either in Grasshopper sort them in some way. Sorting is very complicated. I could sort them vertically or sort them by the x-axis or sort them by length. Sorting is often a big challenge. Or I can just sort them manually. And in Rhino, when you make something, there's a digital signature for when, and it is a timestamp on every object that was created when it was created. So in Rhino's memory, every object is contained in a long list, just like in Grasshopper, and they are ordered in the order that they were created. So you can use this Rhino script that I uploaded. It's called like reorder geometry. There's a Python one if you have a Mac, and there's a RVB if you have a PC. And it just lets you click on a bunch of things in the order. You can just go tools, Rhino script, load. You can add it. It's uploaded on the developable strips thing, reorder geometry. Then you can add it. Some crunch. That's because I have too many things open, and because probably it's trying to fetch it from the internet. There we go. Okay, so you can add it, and then you can just go through selecting things in the order that you want them to appear in your in your script. And this is to remove the process of ordering from the Grasshopper, which is extremely annoying. I hate ordering things. It's like gluing. It's one of the most time-consuming things you can possibly do, is try to get things in the right order. There's always one that is like out of order. Awful. So you can just order it manually once. Hit OK. It'll wait. They'll be all grouped in an order. And then it'll say reorder. And then you can put those in here. And you can put this in here. And it should, if it's on. Yeah, make a bunch of bolts along those curves in an alternating pattern. This has to be a single poly surface. So I joined all of these into one surface, and there were parts that I couldn't join. For example, this part, like there's a part here, this little zone wouldn't join. And if that's the case, I would just, quit and just do it twice. Okay, rather than, I'm trying to say that the goal to automate everything is a fool's errand. Okay, so, but you can see it's doing it on half of it. It's good enough. All right, so this is the same thing, the same exact script that I did previously. I'll just kind of rebuild this again, but there's a little more complexity to it. Okay, so let me turn this all off. I don't know why it's showing this in red. Oh, because it is red. Okay. Let's not make it red. Okay. So now I've got all these curves in here. I've got the B rep in there. Here are my curves. I can do the shorten curve thing. And then what I did here is I wanted every other curve separately. So I used a dispatch, and now I've got two lists of curves, one that's there and one that's here. And then I did again a divide curve, and I'll do it by 20 or something. Let's do it by 20. And let's do this one also. And now let's do another dispatch. and take every other point of this list and every other point of that list. And then we can take the opposite ones of those. And if you look at this, I'm generating an alternating pattern by just doing these dispatches. I took every other curve. They had to be ordered in order to do that. If they were not ordered, it would have been chaos. But I just order them manually, every other one. Then I divide them down, every other one. And now I can do the same thing again. I can merge these. I can do a VREP closest point. And I can draw the normals. Okay, I'm just the same damn thing again and again and again. It's the same script, just adding, like, trying to build up layers of functionality. So if you wanted, you could just make manual points and use the first one. Or if you want to create the pattern, you can create alternating patterns with these dispatch commands, and you can make your own pattern if you want a 2-2-1. Okay, so that makes some sense. Very confusing, I have to say. But like, if you're just watching me do it, but still, I think it's the same process. The limited number of tools that I've already introduced, I think, are sufficient to do this operation of putting bolts onto surfaces or little holes or whatever. This is all you really need, is this line SDL and this VREP closest point to put holes into models parametrically. Okay? Okay. So now I think it's incumbent on me to talk about vectors a little bit. Okay, I don't know how many of you remember this stuff from high school or college, whatever you took in college. But this is, if you want to take computational design here or, study it on your own, you need to remember this stuff. And everything in Grasshopper relies on vectors. Okay, so this is the one thing that I think is important to remember. That's the one piece of background knowledge I think you need for the remainder for all the other computational course sequences that you would need to take in this school. There's scalars, which are just individual single numbers. They can be imagined on the number line. And there's vectors, which we think of as arrows in physics, but they're not really arrows. That's just one way of thinking about them. What they actually are, at least in the computer world, is lists of numbers, and they can be plotted as an arrow like that. And they do not have an origin. They can be plotted anywhere. The list of two numbers represent 2 over, 5 over, 2 up. And the magnitude is taken using the Pythagorean theorem, which is, that is the magnitude of the vector. That is in 2D. There are also 3D vectors, which are just lists of 3 numbers, X, Y, and Z. By the way, they are the same as points. There is basically no difference between a point and a vector. Sometimes we think about a point as a vector from the origin to the point. They are essentially the same. They're the same computationally, the same mathematically. And so you take the magnitude again using the Pythagorean theorem twice. You get that a squared, square root of a squared plus b squared plus c squared. And then you can unitize a vector, which means making its magnitude 1. And that is by dividing every component of the vector by the magnitude. So here the magnitude of this vector 2, 2, 1 is 3. And if I want to unitize the vector, it would be this vector, 0.06667, 0.06667. That is magnitude 1 in the same direction. And so in Rhino, in Grasshopper, very important to very important when you have a vector, like for example, this is a vector, this normal vector. By default, it probably has magnitude 1. But I could, when I put it into a vector, I can right click and go unitize, which will set the magnitude equal to 1. And then if you multiply it by something, you'll know how big it is. In Grasshopper, anytime you want to move anything, anytime you want to do anything, you're always doing things with vectors. So if I go back to my thing here, all of this is vectors. So let's say I wanted to move something. Like move let's turn some of this off. If I wanted to move this B rep, I need a vector. So I could make a vector X, Y, Z, put some numbers in, 25.00, 100.00, 10.00, and then I can use a move, and the move takes the vector. And what you will notice is there's no such thing as copying in Grasshopper. You just move something because it always is copying everything. Okay, so that is the vector. And then, like there are many ways to get vectors. So this is just the dumbest way, this way of inputting the coordinates. Well, I can also make a vector between 2 points. So let's do that with this one. I'm going to put a B rep in here, a different B rep. And then I have a point that I created over here. So if I had a point over here, well, I can get the point using volume. Volume will give me the centroid of the thing if it's closed. Then I can do a point over here. Set 1 point. And I can do a vector 2 point from point A to point B. And then I could do a move. And it's going to be moving its centroid to the place. And typically this would be much more kind of normal seeming than you would think, because let's say I have a curve, let's say I have a funny curve, and I'm going to just divide this curve down into a bunch of points. And then rather than having a manual point here, just move it from its centroid to all the points along the curve and use that. So typically, if I wanted to say copy some geometry around on a surface, that would be how I would do it. I would have a start point and I would have a near the geometry, sometimes created manually. Sometimes I would just have rather than doing this centroid thing, just do a point. And then I have a bunch of points that are created in some other process. I make vectors between them. I use those vectors to move. You can get vectors in lots of ways. Like I said, you can get them with 2 points. You can get them by entering it manually, or you can get it often. You can get it again, from last class, by evaluating the tangents of things. Okay, that's also a vector. So these tangents are vectors, and the normals that you get out of things are vectors. Does that make sense? Okay. So then there's vector arithmetic, vector addition, adding two vectors, tip to tail. This is useful because if you add two unitized vectors, you get the bisector between the vectors. So if you want to move something between two directions, first you unitize the vectors, add them, then you unitize the output, and then you can move something along that direction. There's multiplication, vector multiplication, just multiplication by a thing. So like I was saying, let's say I have this right here. Let's say I have two curves. Set one curve, set another curve. Let's turn all this off. These are two curves. If I just convert these into lines, since they are lines, and then I convert them into vectors, Grasshopper will just do it for me. This is another way to get a vector. First, I have to convert them into lines, then I convert them into vectors. And then if I unitize both of these, and then I add them, and then I multiply by a number like 150, and then I do an SDL from the endpoint, the start point of one of these curves along this direction. Okay, that's the bisector. Yes.
What's the difference between a line and a curve?
A line is defined in the computer very differently. A line is only defined by its endpoints and it's straight. So the computer doesn't store anything except the endpoints. Very minimal mathematical structure, super fast. If you do a curve, it's the whole nerve structure. And so it doesn't quite know how to convert it into a vector. And it won't give you the magnitude of the vector. Sometimes it'll try, but it's a little unpredictable what it'll get.
So if you turned that curve right there, that swooshy one, into a line, it would just like
it might tell me
between the
it
curves.
can't do it, or it might try. Let's try. Set one curve. Line. Yeah, I can't do it. But if I wanted to, I could take its endpoints and I could do a line from the endpoints. Okay. All right. Yeah, it's interesting. It's a different it's a different data structure. So it goes back to this idea of like what I was talking about at the beginning of the classes. The curve class knows different things than the line class. Line class only knows its endpoints. It's all it knows. And it has different functionality, like it can calculate direction, it can know its, length. And then the curve class knows its length in a different way. So this is what I'm showing here. Basically, for me as a person, I can't understand something unless somebody shows me how to implement it. I feel confused unless I am seeing the implementation, what I'm talking about. So there's also this vector display, by the way, which will just display it. So this is just vector multiplication and vector addition in practice. That's all I'm trying to show here. And then if these were flipped, if these lines were flipped, it would do something weird. It only works because they're pointing in the same direction. So this issue of which direction it's pointing is actually another kind of troubleshooting error that comes up. Okay. Does that make sense? All right. Now the dot product. These are the two things that I feel like I actually want to talk about. The dot product, okay? The dot product is trig. Remember trig. These are the trig functions. You spent a whole semester on this in high school. That's it. A squared plus b squared is c squared, the Pythagorean theorem, sine, cosine, tangent, the ratio of the sides. And this is because the sine and cosine and tangent are defined by the Pythagorean. That's why they exist. Okay. So they are the Pythagorean theorem applied to the unit circle, and then the ratios that come out of that, and then they're just put in a big table that your calculator knows and spits it back out. Okay, so the dot product is also called the projection product. And it is defined, it is not, but it is defined by the projection of one vector onto another. And that would be the magnitude of the vector, which we write as its absolute value. That's what we mean by the absolute value. We mean the magnitude of the vector times the cosine of the angle would give you this sum called the projection product. So the projection of A onto B is the magnitude of the vector times the cosine of the angle between them. And that number only depends on the size of this vector. So for the dot product, we multiply it again by the magnitude of B. So the dot product is the absolute value of A times the absolute value of B times the cosine of theta. Or you can calculate it in this other way. It's very important. It's one of the most important things in the world. It's the dot product. Because of this, because it tells you some information about the relationship between two vectors. So if two vectors are pointing in one direction, the cosine of theta is 1, so the dot product is a maximum. If two vectors are pointing, along each other, the dot product is positive. If they're 90 degrees, the dot product is 0. If they are opposite directions, dot product is negative. And if they are completely 180, the dot product is at a minimum. This is how you can tell whether things are pointing in similar directions. And then you can also divide the dot product by its own absolute value and get what's called the cosine similarity. And this was just a number that's either 0 if they're 90 degrees, 1 if they're pointing kind of in a similar direction, or -1 if they're pointing slightly in opposite directions. This is like, I cannot tell you how many times a day I use this. It is so useful. Okay, this is the most useful thing I ever learned as a child. Okay. So like, to give you a very practical example, if I have, let's say, a sphere, and I do set 1 B rep on this sphere, and then I divide surface, and I take a bunch of points, and I draw all these normals. Okay, here's a bunch of normals. Let's make them longer. If I just have a single line, like let's take a line, let's put it in here, and let's convert these to vectors. So let's take the vector here to unitize this. Let's just take these vectors, unitize them, and let's do the dot product. between these vectors and this one vector. So I'm taking the dot product between all these normal and this one vector. And because I unitized them, they will be always numbers between -1 and 1. Okay, so then if I just do greater than, then I can put in here, let's say 0.5. Let's do a smaller number, 0.500. And then I do a dispatch. This is giving me a pattern of true falses. I can put that in here, and I can put these lines in here, and I can take the and now as I drag this, it's telling me which of these vectors are pointing in the direction of the other vector and by how much. Okay, this is so cool. The dot product is so useful. It tells you, I take the dot product of a vector and all the other vectors, and then it tells me I compare it to a number, and it tells me whether the things are positive, negative, 0. That tells me whether they're pointing in the same direction. Okay, this will come up over and over and over again if you ever do a computational design class here. Dot product. Okay, the other one that's important is when I have this in here that's down here, dot products, and then this right here is like a little visualization of the dot product. Then the last one, the cross product. The other one that's very useful, the cross product. Remember the right-hand rule? Find another vector that's always perpendicular to them. Oh my God, so great. The cross product defines a plane also because two vectors define a plane. And it turns out the area, the cross product's magnitude is the area of the parallelogram, where you can do that funny formula, which is also called the determinant, but it's not important. You never need to do it. It's just useful only for finding the perpendicular vector to two other vectors. Do this 20 times a day. Okay. So these are them again. Okay, but examples. Examples. Back to my sphere here. Instead of doing the dot product, let's draw all these normals. Okay, let's make less of them because this is kind of confusing. Instead of doing the dot product, let's do the cross product of this vector and the vector I put in. Okay, and then let's do a line in that direction. Oh my God, look at that. It maps the perpendicular between the vector that I put in and the other vector. Yes. So useful. It is so useful. If you wanted to make, like, if you want to find a direction in space and you have only one direction, the way to kind of convert it into a plane is always by using the cross product. So like if I have a tangent along a curve, and I want to figure out how to align things here, I will often need to take the cross product of this vector with up, and that will give me the perpendicular vector. So I'm always looking for how to define a little frame in space from one vector and orient things in that way. And this is the thing, okay? This dot product and the cross product. I don't know. You don't need to use it for this class, but it will come if you ever want to do anything parametric, they will come up 1,000 times. So you can just go remember them. Okay, they're useful. Okay, so then the last thing, I have 2 minutes. I think I can say it. The last thing is that a plane is defined either by a point, is usually defined by a point and one vector, which is its normal vector, or by two other vectors, which are the vectors that would produce it in the cross product. By the way, what's interesting about the cross product doesn't matter which vectors you put in. It only matters that they're in a plane. These two vectors can be anything, wiggle around, but they always define the same perpendicular vector. Okay? Because two things always define a plane. So, if I wanted to say, like, put something on a surface, let's say I want to put a box on a surface, I need to get this surface, and I need to get a plane so I can evaluate the surface. I can evaluate it somewhere, wrong vector. Somewhere on it, get this little doohickey, and then I can orient from plane to plane. So I can take this BREP, and it needs an origin plane, and it needs a target plane. So I can give it an origin plane. The way I usually do this is I just use the standard world planes, like the XY plane, which takes an origin. So I would just put a point here, put it into the XY plane, and then use that as my source. And it will orient this onto the surface, okay? So this is the other thing are planes. Planes made this way. And I think for the BREPs that I've just been doing where you don't have planes like over here, if that still exists, what you can do is you can do plane origin, and it just, you can do plane normal, and it just takes the origin point and the normal, and then you can map all of these BREPs onto those planes like that. Okay, so planes are normals, plane-to-plane transformations, dot product and cross product, and the BREP closest point. Okay, so the other thing that is in here, by the way, are a few of my other models, like this one is in here. So is the script that puts things unrolled on it. So is the Klein bottle uploaded. You want to look at that. I'm going to go over a few more of these scripts next class that are a little more elaborate, and I'll also start meeting with you. Okay? All right.